Hello everyone, my name is Yu Chen. Today I am honored to present our research. The title is DRCOP, a dataset on real-time commentary in U.S. presidential debates. Our work introduces a novel resource designed to bridge the gap between political discourse and automatic commentary generation. To begin, I will provide some background on the motivation behind this study. In modern democratic societies, presidential debates serve as a crucial platform for political dialogue, enabling the public to better understand the positions and ideologies of various political parties and candidates. However, for the general public, fully grasping a candidate's complete ideology is no easy task, and watching an entire debate can be a taxing experience. Recognize this, many modern media outlets have begun implementing real-time commentary, transforming passive viewing into a highly engaging and contextual-like experience. Like the figure shown on the left, professional commentators serve three critical functions in political communication. First, it enhances usability by decoding rhetorical strategies and translating complex political jargon into insight for a broader audience. Second, it depends understanding by uncovering nuanced meaning that untrained observers might miss. Finally, it provides neutral and clear interpretation, offering balanced, evidence-based insights that help viewers navigate political crises in an era of information overload and media polarization. Debate transcripts are widely utilized in research fields such as argument mining and political psychology. However, existing studies have primarily focused on the context of the debates or social media discussions. There remains a significant academic gap. The lack of a comprehensive dataset specifically integrating real-time professional analysis and commentary on presidential debates. To address this gap, we present real-time commentary analysis in U.S. presidential debates. Past research on political dialogue has primarily focused on discourse structure, factual claims, and argument analysis, which can be categorized into two main directions. The first is fact-checking. Datasets like Trustworthy and CLEF use binary labels to identify statements that require further scrutiny within debate contents. Similarly, ClaimRate provides annotated data using machine learning to prioritize claims for fact checker based on predictive accuracy. The second direction is argument mining and social discourse. The CMU datasets analyzes public reaction by collecting Reddit comments on debates, clarifying claims into four types to bridge the gap between media content and public response. Additionally, MARC is a multi-model dataset including text and audio from the 2020 debates, focusing on argument mining by categorizing discourse into support, attack, or neutral stances. Compared to previous datasets that focus on simple dimensions of dataset debates, DRCOP significantly expand the scope of research. We provide a more comprehensive view of the intersection between expert insights and candidate discourse. Furthermore, DRCOP supports the emerging field of grounding common understanding and generation, while prior research has explored automated news comment generation or translated scientific contents into news narratives. DRCOP provides a foundation for this test within a unique real-time and highly politically sensitive context that allows future language models to be benchmarked on their ability to understand and generate commentary within such time-sensitive and complex political environments. Having discussed the advantages and key features of DRCOP, let's take a closer look at how the dataset was constructed. Regarding the data scope, DRCOP encompasses 10 U.S. election debates held between 2016 and 2024, including presidential, vice presidential, and GOP primary debates. We meticulously align real-time commentary from Bloomberg professional analysis with official debate transcripts sourced from various media outlets. This was then labeled based on their specific characteristics, resulting in a total of 2,284 annotated commentary snippets. Now, let's discuss our labeling taxonomy. As mentioned earlier, we developed 11 labels to categorize the unique characteristics of each commentary snippet. The core logic of our design is to differentiate between objective commentary and subjective commentary. We define 7 major categories, with the commentator's professional opinion category further divided into 5 subtypes, total 11 labels. The objective categories including key summary for summarizing candidate or moderator points, supplementary explanation for providing neutral background information, fact-checking to verify statements, and market reaction for economic trends, and last is public opinion for poll data and sentiments. Regarding subjective and other categories, we have commentator truncheon for topical inquiries, and commentators perform opinion which is further subcategorized into candidate performance, statement analysis, interference and conclusion, marking performance, and other different topics. Moving on to our annotation pipeline, based on the characteristics of expert political commentary from Bloomberg, we developed an 11-category schema for labeling. The annotation was conducted by graduate students with background in computational linguistics. They paired Bloomberg's commentary with the corresponding debate transcript, applied their judgment through shared guidelines and pilot testing. This process ensures high-quality labels, achieving a level of moderate agreement across the datasets. Then, this table illustrates the distribution and statistical characteristics of our annotated data. We can derive three key insights from these results. First, summary functions are dominant, with key summary accounting for 60.84% of our commentary. Although this leads to clash in brands, it faithfully reflects the primary mission of professional commentary during live broadcasts to distill key points and make the debate more accessible. Second, there is heavily reliance on external knowledge. Supplementary explanation at 16.82% and personal opinion at 15.33% are less more frequent. This highlights a significant challenge for automatic commentary generation, as these categories depend on internal context that cannot be retrieved from the transcript alone. Finally, subjective evaluations are concentrated on performance. Within the CPO category, analysis focuses most heavily on candidate performance, while observations regarding market reactions are not properly read throughout the dataset. Next, we authorize the COP to perform several core NLP tests. We define three specific tests to evaluate the performance of large language models in the context of professional political commentary. First, commentary understanding. Given an existing expert commentary, the model must classify it into one of our 11 predefined labels. This test serves as a benchmark for automated labeling and semantic evaluation. Second, commentary planning. Given a segment of the debate transcript, the model predicts which type of the commentary an expert would likely produce. Unlike analysis existing context, the planning test aims to anticipate commentary-worthy segments, facilitating real-time assistance. Finally, commentary generation. Using the debate transcript as a prompt, the LLM is tasked with mimicking a human expert style to generate reasonable commentary. The goal here is to estimate the qualitative and strategic gap between AI-generated content and actual human expert analysis. We evaluated for widely recognized large language models. GPT-4o Claude 3.5 and Gemini 2.0 and DeepSeek are one. These models were selected due to their prominence and widespread adoption in the industry. However, we exclude DeepSeek from the primary generation test to ensure that the parametric scales of the remaining API-based models remain comparable. Regarding our prompting strategy, we tested two approaches: zero shot, providing only one label definition, and few shot, including two examples per label for in-context learning. We also ensured that the semantic meaning of the prompts remain consistent across all models. For evaluation, we use micro-FI and macro-FI scores for the understanding and planning tests. For generation tests, we utilize standard metrics include BLEU, ROOK, and BUSCO to measure the similarity between AI-generated content and actual professional commentary. Since traditional similarity measures often fail to capture the diversity and depth of expert commentary, we introduced a mechanism using LLM as process for general public to objectively score the generated content. Drawing on the concept of use values, we categorized the evaluation into two frameworks: objective summary, focusing on facts, and subjective commentary, focusing on analytical depth. Each dimension is scored on a 1 to 5 score. For the objective summaries, we evaluate efficiency, style, reliability, and comprehensibility. For subjective commentary, we assess importance, comprehensibility, inventiveness, possibility, and reliability. This comprehension framework allows us to benchmark the nuanced capability of different LLM. Moving to our results, this table summarizes the performance of GPT, Claude Gemini, and DeepSeek in the understanding and planning test. Across all models, few-shot prompting consistently enhanced performance in commentary understanding, while GPT-4o emerged as the top performance. Its big macro F1 of 0.4631 indicates that grasping the deep nuances of expert commentary remains a significant challenge for even the best LLM. Notably, Gemini lagged behind other models in both tasks. We also find that planning is significantly harder than understanding. This is because human experts integrate external political context, whereas models are limited to the training itself. Most strangely, in the planning test, a simple majority baseline, always predicting key summary, well-built LM performance. This suggests that training alone has sufficient cues for LM to outperform simple frequency-based guessing. Next, this confusion matrix illustrates GPT's performance in the understanding test. Initially, when corresponding based solely on commentary tests at the left side table, the model frequently confused key summary with supplementary explanation. To address this, we conducted an additional experiments on the 2024 Biden-Trump debates by incorporating debate-centric context. As a result shown in right side table, GPT-4o's recall for key summaries significantly improved from 77.65% to 80.88%, proving that centric context is vital for distinguishing between summaries and background information. In the planning test, using Claude's confusion metric as a representative test, we observed a strong bias toward key summary predictions. This indicates that LLM lack the professional judgment to discern when to incorporate external information. Most critically, the model frequently predicts subjective personal opinions in contexts where human experts remain objective. This highlights a significant gap in the model's ability to master the professional timing and appropriate context for offering subjective analysis. Then this table shows the minimal test results for understanding tests on the left and planning tests on the right. The finding confirms that different LLMs exhibit distinct behavioral patterns. To generate richer and more diverse reviews in the future, strategically combining models with different behavioral profiles is recommended. Moving to the generation test results, we use standard metrics BLU, look, and BERT score to measure the similarity between LM generated and expert reviews. While BERT scores show promise, the low BLU and look scores suggest that traditional word overlay and semantic metrics struggle to capture the lexical diversity and multifaceted nature of expert level writing. To address this limitation of traditional metrics, we introduced a new value evaluation framework. We developed multi-dimensional criteria for key summary and commentary to better align with human judgment and capture content quality. Using an LM as a judge approach, various LM were employed to score the generated output. These two figures present the evaluation result. The top figure focuses on summary performance, while the bottom figure details the commentary results. Two key observations emerge from this result. First, we identify a universal self-preference biases, where all models tended to award higher score to their own generated contents. However, even with these biases, there was a clear consensus across all dimensions of subjective commentary. Every model consistently ranked the human expert reviews as the highest quality. In the final phase, we conducted human evaluation to bridge the gap between LM and human preferences. Two independent evaluators assessed 500 data points using the same multi-dimensional criteria. The results shown in this table for summary on the left and commentary on the right reveal three key findings. First, human evaluators consistently ranked expert written summary highest for their precision and semantic accuracy. Second, among all models, GPT received the lowest human score, indicating challenging in summarizing debate content. And last, notably, Gemini's scoring alignment was the most consistent with human judgment standards. To conclude, I would like to summarize our research contribution and future directions. Our study offered three primary contributions. First, we developed the DR-COP dataset, which aligned U.S. presidential debate transcripts from 2016 to 2024 with real-time professional commentary. Second, this dataset bridged a critical gap in political discourse research by providing a foundation for studying commentary, understanding, planning, and generation. Finally, through intensive pilot experiments, we benchmarked state-of-the-art LLMs, revealing their current limitations in generating deeply insightful and content-rich commentary. Looking ahead, we propose three future research directions. First, we aim to enhance AI-generated political commentary by integrating external knowledge, such as real-time news and policy documents, to produce more context-aware analysis. Second, the DR-COP dataset will support cross-disciplinary research between NLP and social sciences. Finally, we plan to expand our data sources. While Bloomberg provides high-quality analysis, incorporating a broader range of media outlets will introduce greater ideological diversity and improve the generalization capability of future language models. This concludes our report. Thanks for listening.